So we're going to start a little bit now talking about alternating currents. So far we've dealt with direct currents primarily. And so an alternating current is a current that switches back and forth. So basically you can think about it as kind of like being like a battery that sort of, its positive and negative switches back and forth. And so primarily most of the stuff that we deal with at our homes, and when you plug stuff in, it's AC current. So our homes primarily use AC current. And so it's important to understand some basics of that. So again, the current basically switches direction over and over. And we sort of had a few examples that dealt with things that were AC. And so the frequency that it switches is like 60 hertz at home. And so that means it's switching back and forth 60 times per second. And so why? Well, we're going to talk today about the two main reasons. So first of all, it's easy to generate, or sort of natural to generate, alternating current, which we'll try to talk about. And then we'll talk about something called a transformer, which is maybe more important reason why AC is primarily used. And so where we left off, we were talking about Faraday's law, and we had a picture of a generator. And literally what that is it's just a loop inside of a magnetic field that's rotating. And so here we have this sort of carryover picture from last time of this. And so if you remember from last time, our magnetic flux is something like this. So BA cosine of theta. And so in this picture here, this thing is rotating. And so we set it up so that our loop, say, starts here and starts rotating from that point there. And so at that point there, its magnetic flux is the maximum, just B times A. And so if you were to draw the picture, our magnetic field was kind of pointing this way. And then our area vector would look something kind of like this here at that sort of initial point. And again, so this is it's like a three-dimensional loop, or like a sheet of a loop. And what we're doing is we're sort of looking the top point down. So the magnetic field is coming through this loop. And just like last time, as we do this, as the flux through this loop changes, we're going to induce EMF, which will make a current. And so again, this is how you generate this electricity in the first place. And so what we're going to claim is then that our flux can be written this way here. So BA cosine omega t. And so we talked a little bit about this omega and the t. We'll talk about it a little bit again as we go on. And so if you look at this picture here, this angle is changing. So what's in here is going to be an angle, right? An angle measured in radians. And our picture here, as this thing moves from the point we looked at, it moves some angle, and that angle is going to be omega times time. And again, omega is going to be in units of radians per second. Time would be second. And so this turns out to be radians there. And like I said last time, I think this is something that you typically haven't dealt with too much. So we're going to spend a little bit more time just sort of trying to get a better working knowledge of that idea, I think. But once you accept that, which we'll keep talking about it, then by Faraday's law, we can go through here and then just take the derivative of that flux. And then one thing is, so basically, typically what happens is for one loop, that equation is BA times cosine of omega t. But typically, when you do this, to sort of maximize what's going on, you'll put a whole bunch of loops in there. Okay, when you see a generator or something like that, there's usually a whole bunch of loops. And so that N is just what we put in there. So sort of the flux for one of them is BA cosine, and the flux for 100 or whatever it may be would be N BA cosine. And so when I take this derivative, it's not a very tough derivative, but we get this here. So our EMF works out to be here a sine function. So the voltage through this loop, it turns out to be something that naturally alternates. Okay, that sine function is going to be positive and negative at different parts as it goes on. And so we come out of this then with an EMF that's going to naturally go from positive to negative and back and forth. And so it's naturally going to be what we're talking about as an alternating current. And just a little bit, I kind of just want to sort of look at this, make like maybe a little table here. So we'll do time versus the actual flux. So our flux here, we wrote as NBA, again, cosine. Now I'm just going to make an example, I'll make sort of a simple one. So let's say we have this thing's rotating with a frequency of 1/2 revolutions per second. Okay, so this thing's rotating 1/2 revolutions per second, which means it takes 2 seconds to go all the way around. All right, and so if we set that up, our omega, the angular frequency, which again is just the frequency in different units, would be 2 pi and then times 1/2 revolutions per second. So the omega equation is 2 pi times the frequency. It's literally just converting this into radians. And so your omega, in this case, for the example I did, would be pi radians per second. And so over here, then for the particular example I made there, you would put in our equation cosine of pi times time. Now, of course, depending on how fast you want this thing revolving, that would be changing, but just to kind of explore what this sort of means to us, that's a nice example to use. And so what we can do then is just sort of plug in different times. So like at time 0, you put a 0 in there, and you get just the maximum flux. Okay, and hopefully that when omega t is 0, the magnetic field lines are sort of primarily pointing through there, and so that would be the time equals to 0. So this guy would be aligned right here at that time equals to 0, so you'd have the maximum flux coming through. And so now if we start rotating this, we'll do a time of 1/2 of a second. And so for this flux then, we get NBA, and then here would be cosine of pi times 1/2, or cosine of pi over 2, which gives us 0. So after a 1/2 a second, pi over 2, so that's like 90 degrees. All right, so this thing then has rotated from this point, and so now it would be this way here. So it's completely parallel to the B field lines, so there's no magnetic field going through there, so there's no magnetic flux. And we can just sort of keep going. So at 1 second, I would then have NBA cosine of pi, which gives me negative NBA. All right, so this thing now is switched all the way around, so it's kind of flipped, and now it would be oriented this way here. Again, this thing is turning around. And so now it's oriented this way, and so our area vector would still be pointing this way, and so now the area vector and the magnetic field are opposite, and so that's why you get the negative sign. So what was before positive flux would now be negative flux. And then we can just keep going from here. So the next time would be 3/2 of a second. And so you'd get NBA cosine of 3 pi over 2, which is again 0. And so that would be that thing flipping back to where it's 0. And then finally, after the time of 2 seconds, you get NBA cosine of 2 pi, which would give us that maximum. So it's right back again to where it started from. Okay, so questions on that? Like I said, I think typically this omega and kind of sine functions, people haven't seen too much of this, and so it can be a little bit confusing. And of course, I just picked this frequency just to be kind of an illustrative one. You know, in our daily lives, this frequency is more, that starting frequency would be 60 revolutions per second. And so here's like a picture. Your book has diagrams of this, of a real simple kind of generator idea. And so again, you're rotating this loop in some kind of external magnetic field. And again, the EMF you get, the voltage you get out of that is going to be going like this. So it's positive, negative, positive, negative. So the EMF was, again, the derivative of that flux we were just talking about. And so this is where hopefully you can see that it's just kind of natural or simpler maybe to create alternating current. And so that's one of the big pluses. And then here's just the relationship between how we set this up. So again, our flux was this NBA cosine omega t, and then the EMF, that should be kind of a squirrely E there. So you can see that relationship there. And basically it's just the same relationship between a sine and a cosine. So when when you can just sort of see that, like, for the EMF, you get this maximum of the EMF when the slope over here is sort of its steepest, right? And then when the slope over here is 0, you get 0 EMF. And so these are just related again, because this is the derivative of this function over here. Okay, so let's look at this just kind of physically to try to just relate this back to what we were thinking with Lenz's law. And so here's, again, sort of a top-down view of a loop in a magnetic field. So the green lines of the magnetic field, our loop is, rotating with the angular velocity as shown. So at this moment, okay, so you're looking at this loop, and so basically it could be that the current is coming out here, kind of going down here and going in through here, or the current could be coming out from the yellow, going up through the loop and then back over to here. So it's, again, with all these pictures with magnetism, it can be tricky. But in this picture here, which case is the current going in, knowing what we know about Lenz's law? So let's try this and see what we think. Go ahead and call time here. So I'm going to look at this. So I think I agree with the majority. Majority is saying A. And so let's look here. Again, what can be really tricky with these things is visualizing this. So let's imagine that, here's my head. Here's my eye, and so I'm watching from this viewpoint over here. Okay, so you're looking at this loop. And so this, again, if we do our before and after pictures. So maybe there's two lines pointing out at you at 1 second, and then just sort of the next little second as it moves, there should be less lines poking through there. So it's heading towards that place where it's going to be flat soon. So again, sort of looking this way, if you think about it before and after, as it's turning this way, it's going to be having less lines in it, which means what I want to do is I want to have the magnetic field, I want it to look like before, and so I want to sort of reinforce the magnetic field that's there, which would have it coming out of the gray side and in on the yellow side. Again, sort of what the majority had. Questions on that one? I know straight up just visualizing this is pretty crazy, but it's hard to draw this picture. Yeah. Sure. So I'm sort of looking at the loop here. So there's like a loop right here, right? And so as I look at it, the B field's pointing to me, all right? And so as it moves, there'll be less B field going through. All right, so what nature wants to do is it wants to keep the magnetic flux through the same, and so it wants to make a magnetic field pointing at me, which would be, in sort of my picture here, a counterclockwise picture, which in that loop means it's sort of coming out at the top, sort of going down the side and coming in for the bottom part. Does that make sense, Ben? Okay. Okay, and so now, just to see, to sort of hit this home, and we want to try to connect this to what we were doing from before. Let's look at now later on. So here you had the so here, if you look at this, so these pictures are tricky to visualize. And so right here, you've got the yellow down here and the gray down here. And so what's going to happen is sort of a half a revolution later, they'll switch, and you'll have the yellow here and the gray down here. Okay, so it's sort of a whole half revolution switched. And I want us to think about the same picture. Okay, so you're looking at the same loop as you were this one, just it's sort of a half revolution to the other side. So now, which way will this be going? Okay, so think about this with your neighbors and see what you think. Is good? So it's actually, it's a little bit tricky. It's actually, if you just disregard the colors, it's the exact same picture, right? That loop is again, it's right here. So if it's in front of me, the loop is turning, so there's less magnetic field coming through there, all right? And so you want to sort of make that magnetic field stronger, all right, by having a counterclockwise. So again, if you look at sort of, it's coming in out at the top, down the side, and in at the bottom. But because the loop has changed by a half, what that means is the current, according to the loop, is going in a different direction. Okay, so because because the loop has rotated, and so what I'm trying to get you to see here is that just by using our Lenz's law, we can see this nature of the alternating current. Okay, so it's sort of going one way in the first case, and it's going the other way in the second case. All right, but again, that can be tricky to visualize. Questions on that? So it's nothing, necessarily new. It's just we're sort of applying it to a different situation. But this really just is applications of Lenz's laws and Faraday's law all over again. Okay. Okay, great. So here's one. I thought we'd try this. We don't a lot of times do numerical exercises, but let's take a few minutes here. So this is like an old test question for this type of material. So a generator exists as below. So it's, again, really hard to draw these things, but you've got that similar sort of shaped loop, and it's rotating with some angular velocity. It's got a total of 10 turns. It's got a certain area of 0.01 meters squared, and the magnetic field is 0.1 Tesla, and it's set up in a circuit with a light bulb. So it's kind of like that one we had in class the other day. So you're lighting up a light bulb with this. And so what we're saying is the light bulb will burn out if the current through it is bigger than 0.5 amps. So what is the maximum rate at which the coil can spin so that the current does not exceed this limit? So discuss this with your neighbors and see what... Okay. So hopefully you've had a chance to think about this one a little bit. Again, I just wanted to kind of... It's always good to just at least try starting one of these things. And if you look here at the answers we got, so the two big ones are A and C. So I agree with, or I sort of see where both of those come from. So the actual answer is, in fact, C. Okay, so let's go through and talk about this. So first, what's going on here is you've got V equals IR. Okay, so you look at this light bulb and you say, okay, well, the light bulb, the maximum current, we're saying before it burns out, is 0.5 amps, and its resistance is 200. And so when I go through and do that, I get that what we're saying is that the light bulb can have a maximum of 100 volts through it. Okay, and so then what you want to use is you want to say, okay, well, we have this equation for our EMF. In a case like this, and our equation was this NBA omega. Now the thing is it's times cosine, right? But that NBA omega, that's the maximum that this value can be. So it seems like a lot of people got that idea. So that's the good thing. So sort of okay, so E max is NBA omega. And so that's the maximum that let me write this. I'm sorry, I'm having trouble writing this so it looks legible. Omega. And so what we want to do is we want to equal that to 100 volts. And so I think if you got 1, okay, if you solve for omega, all right, that answer there, you get omega equals 1 times 10 to the 4 revolutions per second. So what did the person who wrote this one do that's really jerky? Is that they wrote the answers in frequency F, okay? So in frequency F, which, the book problems tend to do that. They tend to want you to get really good at converting that back and forth. And so if you take omega divided by 2 pi, all right, then you come out with this answer for frequency in revolutions per second of the 1.6 times 10 to the 3rd revolutions per second. So I just kind of wanted to do that again, just to sort of hit this thing home, because I think a lot of us don't, in general, have a super lot of familiarity with that. Questions on this one here, anybody? Okay. And so then just to kind of wrap up this section on generators, so again, here's our EMF equation. And so what will often sometimes happen, so there's actually a problem on our discussion sheet tomorrow having you kind of walk through this. So this would be the EMF. Now if you want to find the current, right, that's typically sort of the next step in a lot of these problems. And it's usually just a matter of dividing by the resistance. So you divide it by that R, right? And then now we've got this current in this loop. Anytime there's a current going through something in a magnetic field, you can have a torque. Okay, so we talked about this. This is one of those things where we sort of showed this equation briefly. I think there was like 1 or 2 book problems on it. But there's a torque on this loop caused by the magnetic field. And so it looks like this. It's the N times the area times the B field times the particular current that's in there. And so what you can do is just plug in your value for the current. Okay, and this is just sort of trying to set you up a little bit for this problem and discussion tomorrow. And so this is the torque. But the main idea is, like with a lot of these kind of problems, is that if you're sitting there rotating this, say, to make this electricity, to generate this electricity, there's this torque that's constantly trying to spin the loop down. Okay, and so you have to supply an external torque to keep it spinning at this constant omega, right? So you don't just get sort of free energy. You've got to be putting this torque in, so you've got to be driving this thing here. And so there's something always, in this case, going against you. Okay? But again, we'll sort of deal more with that a little bit on your discussion sheet tomorrow. So I just wanted to kind of get ahead of that a little bit.